Okay, hello again. This is chapter 14, and these are the questions and answers on the chapter on rates of reactions. So, you've done these questions. Were you able to do all of them? Let's go through the first one. The first one gives you an information about hydrogen peroxide, and he's saying the reaction is faster when manganese oxide is added. The manganese oxide remains chemically unchanged. Once he tells you that when I added the manganese dioxide, the reaction is faster. The manganese oxide remains unchanged. That means that the manganese oxide was what? The manganese oxide was a catalyst. A student investigated the reaction in the presence of manganese oxide. He collected the oxygen gas produced, recorded its volume every 5 minutes. He has these results. The volume of gas given off between 5 and 10 minutes is 12 centimeter cubed. Calculate the volume of gas given off between 30 and 35. How did you get the volume of gas given off between 30 and 35? At 30, the volume of gas in the syringe was 58. At 35, the volume was now 60. So the volume collected between 30 and 35 is just the difference, right? So that's just 2 centimeter cubed. So he says at 5 minutes, between 5 and 10 minutes, he was able to collect 12 centimeter cubed. But between 30 and 35, he was able to collect only 2 centimeter cubed. So explain in terms of the changes in the rate of the reactions and collisions between particles why your collected volume is less than 12 centimeter cubed. As the time goes by, the amount of gas collected in the 5 minutes is less. Of course, this is because we said as time goes by in the reaction, the rate slows down since the hydrogen peroxide particles are being used up, so there are less collisions. Remember that he says explain in terms of rate and collisions. So the rate slows down. This is because the hydrogen peroxide particles are being used up, so there are less collisions per second. After how many minutes did the reaction finish? Well, we look at the table and we see when did it stop giving out any gas? When did the volume of gas stop increasing? So look at the table, and it kept increasing until what? Until 35 minutes, it's 60, 40, it is still 60, so that means that the reaction finished after 35 minutes. What type of substance is manganese oxide again? He says that when he added it to the reaction became faster and the manganese oxide remained unchanged. That is definition of catalyst. So manganese oxide is a catalyst. Okay. Some of the graphs A to F below could represent changes occurring during the decomposition of the hydrogen peroxide. So he gives you 6 graphs A, B, C, D, E, F, and he says which graph could represent the total mass of oxygen given off as the experiment proceeds. So which one gives you the mass of the gas as the experiment proceeds? Remember that at the beginning there is no gas at all, and then as the reaction proceeds the gas increases, and then at some point it stops increasing because the reaction has finished. Which graph indicates that? Of course, graph C. Can you see that it's graph C? So if I draw a graph of the mass of oxygen given off from the experiment, or plot the points that he showed in the table, I would get graph C. These are the same graphs, and the next question says which graph could represent the mass of hydrogen peroxide as the reaction proceeds. So what is happening to the mass of the hydrogen peroxide? The mass of the hydrogen peroxide is being used up, so the mass of the hydrogen peroxide should decrease until there is no more hydrogen peroxide. So which graph tells you that? Graph E. Do you understand that? The other question with the same graphs, and he says which graph could represent the mass of manganese oxide. Remember that we said the mass of manganese oxide is a catalyst. Definition of catalyst is a substance that speeds up the reaction without being used up. That means if I start with a certain mass of manganese oxide, I should end up with the same mass. So which graph tells you that? The graph where the curve is a straight line, or the graph is a straight line. Okay, so that is graph A. Can you see that? Okay, for this next experiment, he has potassium iodide reacting with lead nitrate. He gives you the equation, and he carried out the investigation to find out how much precipitate was formed. So the lead iodide, he tells you from the equation that the lead iodide is a precipitate, an insoluble salt that is formed. So he used a measuring cylinder to transfer 15 centimeter cube of potassium iodide into a clean boiling tube. Using a different measuring cylinder, he measured out 2 centimeter cubed of lead nitrate solution and added this to the potassium iodide. So now he is adding the lead nitrate to the potassium iodide, so he should see a precipitate. A yellow precipitate formed in the tube and was allowed to settle. And what he's measuring is he's measuring the height of the precipitate every time he adds the lead nitrate. So what we have is, he has in the test tube 15 centimeter cubed of potassium iodide. So every time he's adding, he just has the 15 centimeter cubed of potassium iodide. And what he's doing is, he's measuring out more and more lead nitrate. He repeated the experiment using different volumes of lead nitrate. So every time he has a certain amount of potassium iodide, 15 centimeter cubed, but every time he's adding more and more lead nitrate. In each experiment, potassium iodide solution and lead nitrate solution he used were of the same concentration, and the graph shows the results. So he already drew the graph for you. He already drew the graph for you. Sorry. Explain why the line on the graph rises to a maximum level but then does not change. So he has a certain amount of potassium iodide in the test tube. He has 15 centimeter cubed of potassium iodide in the test tube. And when he added, for example, 2 centimeter cubed of lead nitrate, he had a certain amount of precipitate. When he added 4, he had a certain amount. When he added 6, he had a certain amount. When he added 8, he added a certain amount. After that, the more and more lead nitrate he added, no more precipitate was formed. Of course, because I have a certain amount of potassium iodide that will react with a certain amount of lead nitrate. If you then go on and add more and more lead nitrate, then the lead nitrate you're adding is just excess. So what you have is, as more lead nitrate is added, more precipitate is formed until all the potassium iodide has been used up. The reaction finishes, no more precipitate can be formed. So you're just adding more and more lead nitrate, but that is excess because the potassium iodide has finished. So on the graph, circle the point which seems to be anomalous. Of course, we said anomalous means away from the curve. So you put a circle around that point that is way up there at 12 centimeter cubed of lead nitrate and 4 centimeter of height. Can you see that up there? Okay. Explain 2 things that the student may have done in the experiment to give this anomalous result. So I look at the anomalous result and I find that it is way above what the line should be, what the curve should be. So what does that mean? That means either I added too much potassium iodide in the beginning. I was supposed to add 15 centimeter cubed of potassium iodide in each experiment. Now maybe the student at this in this experiment, he added too much potassium iodide, so too much precipitate was formed, or more precipitate than you should have obtained was formed, or the test tube was not left long enough for the precipitate to settle down. So when he measured the height of the precipitate, it was more than it should have been. Do we understand these? So we're talking about this because he got much more precipitate than he should have got. Okay, the diagram shows the result of an identical experiment. So he has the precipitate of solid lead iodide down there, and he measures the height with a ruler. So how much precipitate has been made? So you just look at the level of the precipitate with the level of the ruler. So this is 1.5 centimeter. Use the graph to find the volume of lead nitrate solution needed to make this amount of precipitate. So I look at the graph, so that is the graph again, and I look at, I have 1.5 centimeter of precipitate, so I look at the height of precipitate is 1.5, I go to the graph horizontally, I go down, I find that I must have added 3.8 centimeter cubed of potassium iodide. Were you able to do that? Okay. The next experiment says hydrogen can be prepared in the laboratory by reacting zinc with dilute sulfuric acid using the apparatus shown. The equation for the reaction is this. The reaction is fairly slow, but when copper 2 sulfate is added, bubbles of hydrogen form. The bubbles of hydrogen form much more quickly. That must mean that copper sulfate is catalyst. Okay, a student decided to investigate how copper sulfate solution increased the rate of this reaction. She set up the apparatus as shown without copper sulfate present and counted the number of bubbles of hydrogen produced every 15 seconds. She then repeated the experiment with the copper sulfate present. Explain why her method of counting the number of bubbles of hydrogen might not give accurate results in her second experiment with copper sulfate present. Remember that what she's doing is she's not collecting the gas in a gas syringe. That would have been a much better way, and measure the volume of the gas. That we said that is the best way to measure the volume of a gas given off. What she was doing is she was collecting the hydrogen over water and she was just counting the bubbles. Now, at the beginning, if the reaction is slow, you can see the bubbles going out. So you can count them, 1, 2, 3. But what if when you add the copper sulfate, the reaction is very fast? Will you be able to count the bubbles as they come out? So, why the method of counting number of bubbles might not give accurate results in her second experiment is that with the copper sulfate, the reaction probably will be too fast. So the bubbles will be coming out very quickly. So counting the bubbles would be more difficult. Okay, were you able to think of that? Okay, so try to think of, first of all, in your actual exam, you cannot leave any question empty. You have to think of it. So a question like this, you should think of what could probably be the answer and try and give a reasonable answer. I'm going to remind you again that in the Edexcel exam, you're supposed to write in black ink. So please don't mind the blue that I put. I use blue just to make it clearer for you. But in the actual exam, you're supposed to use black ink. Okay, the next question says, describe how she should change the experiment to allow the collection of more precise results. Of course, we said if I want to measure volume of gas given off, I should measure it using a gas syringe. That would be the more accurate or more precise way of getting a good result. Okay, some students investigated, this is another experiment, some students investigated the rate of reaction between sodium thiosulfate and hydrochloric acid. The precipitate of sulfur makes the reaction mixture go cloud. Remember that this was the experiment that we talked about when we were talking about a reaction that gives a precipitate. We said if I put sodium thiosulfate with an acid, it gives sulfur, and sulfur is a yellow solid. So the reaction becomes cloudy. Now the students use this method. Place a mixture of sodium thiosulfate and water in conical flask, add some dilute acid, hydrochloric acid, swirl the mixture, start a timer. So she's going to put the flask over a black cross marked on a piece of paper and record the time taken for the cross to disappear when viewed from above. You remember that when we talked about the explanation? Okay, the students used 10 centimeter cubed of dilute hydrochloric acid in each experiment. So they repeated the experiments using the same amount of dilute hydrochloric acid. They carried out all the experiments at the same temperature. So what were they changing? You have to check what were they changing. They used different volumes of sodium thiosulfate. So they were changing the basically the concentration of the sodium thiosulfate, because they were changing the volume of sodium thiosulfate with respect to the water. So they either add too much sodium thiosulfate and less water, or less sodium thiosulfate and more water. So they're basically changing the concentration of the sodium thiosulfate. They were told to keep the total volume of sodium thiosulfate solution and water constant, because in order to check when the X disappears, and compare them to each other, the total volume of solution in the flask should be the same, so that should not change, that should not be a factor that changes. So this is what they did. So experiment in student 1, he used 50 centimeter cubed of sodium thiosulfate, no water, and he measured the time for the X to disappear. The second student used 40 of thiosulfate, 10 of water. The third one, 35, 15, 30, 20, 25, 20. Now, he's saying, explain why the results of student 7 should not be used. What were you able to come up with? Remember that he said the total volume of solution should remain the same. So, for all the students, the total volume of solution was what? 50, 0, 40, 10, 35, 15, 30, 20, 25, 25, 20, 30, all of these, the total volume was 50. But what about student 7? He used 15 and 40. So that means that the total volume is more than 50. So the problem here, I cannot use this experiment and compare it to the others because his total volume is 55, not 50 as the other experiments. Then we plot the results of the 6 other students and draw a curve of best fit. So this is the plotting that you should have, small x's, and you join them with a curve going through all of them as much as possible. So this is the curve that you should get. Were you able to do that? That should be easy. Then he says the students use this equation to calculate the rate. So he said the rate is 1,000 over the time. Calculate the rate for student 1. So what was the time for the student 1? The time for student 1 was 26.6. So that means that the rate is 1,000 over 26.6, and that comes out to be, 37.6. Did you get that answer? Okay. So he gives you the equation and just put in the time taken for student 1, and that's your answer. Another group of students used the same method but with different solutions of sodium thiosulfate and hydrochloric acid. They calculated the rate. So this graph is doing the same thing, but it is calculating the rate or plotting the rate versus the concentration. So describe the relationship between rate and concentration. What is the relationship between rate and concentration? As concentration increases, rate increases. So that's one point. And the fact that it is directly proportional, that means it's going all straight till the end, so that we say the graph is directly proportional. You know what directly proportional is. Okay, explain why increasing the concentration has this effect. So as I increase the concentration, the rate increased. Remember why? Because as concentration increases, I have more particles, so more frequent collisions. Collisions alone is 1 mark. So more frequent collisions or more probability of having collisions since you have more particles moving around in the solution. Okay, this question says an excess of dilute hydrochloric acid was added to a lump of calcium carbonate. So remember which one is excess. When you read these questions, remember which one is excess. If he says that dilute hydrochloric acid is excess, that means it is the calcium carbonate that is determining when the reaction finishes. So once all the calcium carbonate has been used up, that's when all the reaction finishes. The mass of the beaker and contents was recorded every 30 seconds. So this is a reaction, acid with carbonate. If you remember from the chapter of acids and bases, acid with carbonate gives carbon dioxide gas. Now, he's not using a measuring cylinder to measure the volume of the gas. He's using the method of putting the beaker on the balance and measuring the mass of the beaker every 30 seconds. And we said since a gas is being given off, then the mass will gradually decrease until all the calcium carbonate, for example, has been used up, and then no more gas is given off and the graph becomes flat. Okay. Okay, the equation for the reaction is this. So you can see that carbonate with acid gives carbon dioxide gas. And he's saying state 2 observations that can be made when dilute hydrochloric acid is added to calcium carbonate. So calcium carbonate is a solid and it gives off a gas. So any reaction that gives off a gas should give bubbles of gas. And if you're starting with a solid and all the reactants are either aqueous, all the products are aqueous, no precipitate or anything, that means that the solid that you start with will start to dissolve and disappear. So the solid carbonate dissolves in the solution to form the calcium chloride, which is aqueous. Describe the relationship between the mass of the beaker and contents and the time. So what was happening to the mass of the beaker? We said from the graph, the mass of the beaker is decreasing as time increases. So as time increases, the mass decreases, and we said till some point it becomes constant. After how many minutes did the reaction stop? After how many minutes did the reaction stop? We said the reaction stops when it stops decreasing, when the graph stops changing. So where did the graph stop changing? At around 3.3 minutes. Okay? When the graph stopped decreasing. That is 3.3 minutes. State why the reaction stopped, and we said he had calcium carbonate was the limiting reagent, so all the calcium carbonate was used up. Don't say all reactants, and definitely don't say all the acid, because the acid was excess. Okay? Identify the compounds other than water present in the solution in the beaker after 2 minutes. We remember that we said the reaction finished after what? The reaction finished after 3.3 minutes. So after 2 minutes, the reaction has not finished. So he's asking what is present in solution other than water that you will have after 2 minutes. Remember that what you have would be calcium chloride that has been formed and hydrochloric acid, which was excess. I have a lot of hydrochloric acid which is excess in solution. You don't mention the calcium carbonate because that's a solid, but the calcium carbonate has changed. Some of the calcium carbonate after 2 minutes has changed into calcium chloride, and I still have the excess hydrochloric acid that is in solution. So what about after 5 minutes? After 5 minutes, the reaction has already finished. What do you have in solution? You will also have the product, which is calcium chloride, and you still have excess hydrochloric acid because he put too much hydrochloric acid, so you will still have hydrochloric acid in the solution. Were you able to figure this out? You should be able to sit down and think about this. Okay? The experiment was repeated using the same mass of calcium carbonate, but as a powder instead of a single lump. And we said, if I use powder instead of lumps, that means powder means larger surface area, and that means the rate will be faster, and that means what will you draw on the graph? If the reaction is faster, that means it goes down faster, and that would be your graph. So you go down faster, but you should end up with the same final mass of the beaker. Do you understand that? It's just that it is a little earlier. So instead of the reaction finishing at 3.3, as we said, now it's finishing at something like 1 point something, 1.5, for example. Okay? So that is your graph for the faster reaction. This is a recipe for making plum wine. Dissolve 1.5 kilograms of sugar in 5 decimeter cubed of warm water. Add yeast and 8 kilograms of plums. Remember that plums are things that have sugar in them. When you add yeast to sugar, this is the fermentation method. So this is a method of fermentation in order to get wine. Pour the mixture into a flask. Leave the flask for several weeks until the reaction has stopped. Remove the solid yeast and pour the clear liquid into bottles. And we said this kind of reaction is made in a flask connected to an airlock. You remember when we mentioned airlock in the experimental techniques in the second chapter? We said the airlock, what is the function of the airlock if he asks? We said the airlock is something that allows the carbon dioxide to go out, because when this reaction happens, it forms carbon dioxide. When fermentation happens to make wine or to make ethanol, carbon dioxide gas is allowed to go out, but no oxygen is allowed to go in because the yeast needs to work without oxygen. Now he tells you sugar contains sucrose. When yeast is added, water reacts with sucrose to form glucose. Write a chemical equation for this reaction. So he says I have the sucrose, which he gives me the formula of, plus water to form glucose, and that's it. And then you balance. You have to balance. You will need to put a 2 in front of the glucose in order to have it balanced. Okay? The glucose is then converted into ethanol by this reaction. So this is the reaction that gives the ethanol, which we call wine, and carbon dioxide gas. How would you know when the reaction has stopped? Remember that we said if something gives off a gas, the reaction stops when no more bubbles of gas. How could the solid yeast be removed from the mixture? How do you remove a solid, an insoluble solid, from a mixture? By filtration. Okay. Now, in this question, a student investigates how temperature affects the rate of reaction between two colorless solutions containing ions. When he mixes the solution, a reaction takes place between the ions, and after a while, the mixture suddenly turns blue. He performs the experiment at 5 different temperatures, and on each occasion, he's measuring the time taken for the mixture to turn blue. So, first of all, he says plot the results, temperature versus time. Remember that for any graph, if he has the table like this, whatever is on top goes down, and whatever is below in the table goes on the y-axis. If he did not label the axis for you, sometimes he will give you the graph without labeling the axis. So you should know that anything, if the table is this way, then anything on top goes on the x-axis, which is down in the graph, and anything below that goes on the y-axis. So you have temperature on the x-axis, time taken in on the y-axis, and you plot the graph, and he says draw a curve. So when you plot the graph, you will find that you will have x's somewhere like this. Plot the results and draw a curve of best fit. So your curve should look like this. Okay? Then use your graph to estimate the time taken for the mixture to turn blue at 50 degrees centigrade. So in your graph, you look at where 50 degrees centigrade is, you go up to the graph, you go horizontally, and you find that that comes to 120 seconds. What does the graph show about the relationship between temperature and time? So the graph we have, where is temperature and where is time? So what is happening? As the temperature increases from 20, 30, 40, 50, the time decreases. So as temperature increases, time decreases. Explain in terms of particles why an increase in temperature increases the rate. Of course, we said when time decreases, that means the rate is increasing. So why is it that when I increase the temperature, the rate increases? You remember the explanation? If you don't remember the explanation, please go back to the notes. You should be able to explain all of this. We said at a higher temperature, particles gain more kinetic energy, move faster, collide faster. Okay? Particles gain more kinetic energy, move faster, collide faster. State a variable that must be kept constant for the experiment to be valid. So I am changing temperature. What should I keep constant? I should keep same concentration of solutions, for example. Okay? A student investigates the reaction between dilute hydrochloric acid and marble chips. She uses this method. Put 50 centimeter cubed of dilute hydrochloric acid into a polystyrene cup. Measure the initial temperature of the acid. Add 5 grams of marble chips to the acid and stir. Measure the temperature of the mixture after 2 minutes. So she's putting a certain amount of hydrochloric acid into the polystyrene cup. She's adding the marble chips and she's measuring the difference in time. She carries out the experiment 3 times using, what is she changing by? She's changing different sizes of marble chips. So experiment 1, large marble chips, he gives initial temperature and final temperature. And experiment 2, medium marble chips, initial temperature and final temperature. Experiment 3, small marble chips, initial temperature and final temperature. Were you able to fill these this table? This table should look like this. Okay, so the temperature changes for experiment 1 is 1, for experiment 2 is 3, and for experiment 3 is 4. Were you able to do that? Explain why the temperature change in, of course, when you have more temperature change, if you have these are using the same amounts of acid and same amount of chips, but the different sizes of chips. So if you remember, experiment 1 had large pieces, then medium pieces, then smaller pieces. The more the temperature change in 2 minutes, remember that he's measuring temperature change in 2 minutes, the faster the reaction, right? So he's asking, explain why the temperature change in experiment 2 is greater than the temperature change in experiment 1. So if you remember, in experiment 2, you had smaller chips. So the smaller chips have larger surface area, so more collisions, so more energy is transferred to the water. Do we understand that? And if the reaction is faster, that means that was because you had more surface area, more collisions. And when you have more collisions, that means that the reaction will give more energy transferred to the water. Experiment 3 is repeated using 100 centimeter cubed of dilute hydrochloric acid instead of 50. And this is a common type of question. He did the experiment using 50 centimeter cubed and he got a certain temperature rise. What if he used double that volume? What will happen to the temperature change? Remember, if you're heating a certain amount of water, remember that the reaction is something that's giving out heat. So if you're heating a certain amount of water, a small amount of water, you'll need just a small amount of heat to heat it to a certain temperature. But if you have a large volume, it will need more heat to reach the same temperature rise. Or if you're giving it the same amount of heat, then it will not heat up the large volume as much as it heated up the smaller volume. Do you understand this idea? So if I'm doing the same experiment that is producing the same amount of heat, but instead of doing it in a volume of 50, I'm doing it in a volume of 100, that means I'm using the same amount of heat to heat up a larger volume. My temperature change will be smaller because you're using the same amount of heat to heat up a larger volume of solution. So the increase in temperature of the 100 centimeter cube will be much smaller. So temperature change is lower since the same amount of heat is used to heat up a larger volume or a larger amount of solution. Methanol can be converted into methanol. A mixture of methanol and oxygen is passed over an iron oxide catalyst. Methanol and water are the only two products. Write a chemical equation for the conversion of methanol into methanol. So first of all, he's saying I have methanol and he gives you the formula. And he says it's reacting with oxygen. Now he's passing it over a catalyst. Do we include the catalyst in the equation? We do not include catalyst in the equation. The equation is showing reactants to give products. If we're using a catalyst, the catalyst is not included in the equation because it's not a reactant. So methanol plus oxygen to give the methanol, which he gives you the formula of up there, plus water. He says methanol and water are the only two products. And then you balance. When you balance, you'll find that you will need this kind of balance. Are we okay? What is meant by the term catalyst? Remember that we said a catalyst is a substance that speeds up the reaction without being used up or while remaining unchanged. Explain how a catalyst works. Remember that we said a catalyst speeds up the reaction or increases the rate of the reaction. Why does it do that? It provides an alternative pathway with a lower activation energy. Remember, we said catalyst. It increases the rate. How does it increase the rate? Because it provides an alternative pathway. That means that the reaction is going to go in a different method. And this new way has a lower activation energy. And that is why the reaction is fast. Okay. Sodium thiosulfate solution and dilute hydrochloric acid react together slowly to form a precipitate of sulfur. This precipitate eventually makes the mixture go cloudy. A student uses this method. Place 20 centimeter cubed of sodium thiosulfate and 20 centimeter cubed of water in a conical flask. Remember that the order of putting these things is usually like this. You're trying to react sodium thiosulfate with hydrochloric acid. So you don't put the sodium thiosulfate and hydrochloric acid first and then you add the water. That's not right. Because once you add the sodium thiosulfate and the hydrochloric acid, the reaction starts. So you need to leave one of them till the end. So either you put sodium thiosulfate and water and then the acid, or the acid and water and then the sodium thiosulfate. But usually it is sodium thiosulfate and water, and then you put the acid, and then you put the flask on a piece of paper marked with a black X, and you measure the time taken for the X to disappear. Okay, the equation for the reaction is this. Again, we said when you put sodium thiosulfate with acid, it gives sulfur, which forms a yellow precipitate, and that makes your reaction cloud. Before starting her experiments, the student considers the risk to her of sulfur dioxide escaping from the flask. She uses this information. Concentration of sodium thiosulfate is this, volume of sodium thiosulfate is this, volume of water, and volume of acid. Now, calculate the mass of sulfur dioxide formed in this experiment. How do we calculate the mass of sulfur dioxide formed? Do you remember the calculation? The number of moles of sodium thiosulfate, he gives me concentration and volume, so I use concentration times volume. That comes out to be 0.006 mole. The number of moles of sulfur dioxide is from the equation. I go back to the equation, and the number of moles of the sulfur is the same as the sulfur dioxide, is the same as the number of moles of the sodium thiosulfate from the equation. So that would be the same number. And the mass of sulfur dioxide formed in this case is the number of moles times its MR, the MR of sulfur dioxide. So that comes out to be 0.38 grams. Now he's saying the solubility of sulfur dioxide at room temperature is 100 gram per decimeter cubed. Use this additional information to explain whether sulfur dioxide gas escapes from the flask. Remember that here he's putting what? He's saying if I have 100 grams of sulfur dioxide in 1 decimeter cubed of solution, then the sulfur dioxide will more than that. So till that it is soluble. If I have more than that, then the sulfur dioxide will not dissolve anymore and it will go out of the solution. When we calculated here, we found that I have 0.38 grams, but it is 0.38 grams in a total volume of what? What is the total volume that we have in here of solution? We have thiosulfate is 20, the water is 20, the hydrochloric acid is 10. That means I have a total solution in my experiment of 50. That means what I have is 0.38 grams sulfur dioxide in 50 centimeter cubed. Okay, use this additional information to explain whether the sulfur dioxide will escape. So I want to know, do I have more than 100 grams per decimeter cubed? Because if I have more than 100 grams per decimeter cubed, then the sulfur dioxide will not dissolve anymore and it will go out. So I calculate, I have my total volume is 50. That means I have 0.38 grams in 50. So how much in 1,000? You understand this? He wants per decimeter cubed. 1 decimeter cubed is 1,000 centimeter cubed. So what I have is 0.38 grams dissolved in 50. So how much will I have dissolved in 1,000? And I calculated to be 7.6 grams. 7.6 grams is less than 100. So that means that the 7.6 grams per decimeter cube that is formed will just remain in the solution. It will not escape, so no SO2 gas escapes from the, it's not the class, from the reaction. Okay, from the flask, not the class, sorry. Okay, at what point in the experiment should the student have started a timer? When should the student start a timer? We said we start the timer when we add the acid, because he had already added the thiosulfate and water. Once I start adding the acid, that's when I start the timer. She repeats the experiment using the same volumes and concentrations of solutions, but at different temperatures. The graph shows her results. The result at 14 and 4.2 is anomalous. So where is 14 and 4.12? That's the one below the graph, between 10 and 20. So explain one mistake the student may have made to cause this anomalous result. Again, we said if I have an anomalous result, I look at it. Is it below what I should have gotten or above what I should have gotten? It's below. The anomalous result is below the graph. So that means that for that anomalous result, he got a result less than what he should have gotten. So what problem could have happened? He started the timer too late. That is a possible answer. Remember that for this kind of questions, several answers may be possible. If you come up with a reasonable answer that will explain why the result is less than what it should be, that's fine. But the common answer would be that means that he started the timer too late. Use the graph to find the time taken for the x to be no longer seen at 35. So in the graph I see 35, I go up to the graph, I go horizontally, and I find that that takes 20 seconds. Okay? The student repeats the experiments using nitric acid instead of hydrochloric. She records the time for the x no longer to be seen, then uses the times to calculate the rate. So this graph is showing the rate, not the time. Remember that the rate is opposite of time. So something that has higher rate takes less time. So suggest two reasons why the results are least accurate at higher temperature. What is he measuring? He's measuring the time taken for the X to disappear. At high temperature, the rate is too high. So why do we get wrong results when the temperature is very high? So one reason is the fact that the time is too short, so I don't have time to measure the time. Okay, so the time is very short. Or you have, because at higher temperature the solution is hotter, so there is a greater chance of losing heat to the surroundings. Okay, the student wrote this explanation for the shape of the graph. As the temperature increases, the rate of reaction increases. This is because there are more frequent collisions between particles of reactants. Use the particle collision theory to explain another more important reason for the increase in rate. Remember that we said at higher temperature, the rate increases. Why does the rate increase? We said more particles have energy greater than activation energy, so more collisions are successful. Remember, he already says the part where the particles have more kinetic energy, move faster, collide faster. So he has already said that. And the other reason is because when we increase the temperature, the particles have more kinetic energy. So that means that more particles have energy greater than activation energy. Remember that we said activation energy is the minimum amount of energy needed to start the reaction. So the particle has to have activation energy or more in order to have successful collisions, in order to collide and react. Okay? Another student uses the same reaction to investigate the effect of changing the concentration of sodium thiosulfate solution on the rate of reaction. Give three variables. So what is she trying to determine? She's trying to determine the effect of changing the concentration of sodium thiosulfate. So she will be changing the concentration of sodium thiosulfate. Now, what should she keep constant? She should actually keep everything else constant. So something like same volume of acid, same concentration of acid, same temperature. Okay. Okay, this question says the equation for a reaction that occurs in the manufacture of nitric acid is this. Deduce the effect of changing the conditions as shown in the table. Choose from the words increased, decreased, or unchanged. Remember that he's asking for effect on rate and effect on yield. Now, if I increase temperature, what is the effect on the rate of the reaction? We said always, for any reaction, when you increase the temperature, the rate increases. Okay? What is the effect of increasing temperature on the yield? Remember that the yield means I need to look at the fact that it is reversible, and I need to look at where we have exothermic and endothermic, because we're talking about increasing temperature. So is the forward reaction exothermic or endothermic? The delta H is negative, and that means that as I form the products, the reaction is exothermic and gives out heat and heats up, temperature rises. And we said in that case, if I increase the temperature, we said increasing the temperature in a reversible reaction, the reaction goes to the side that is endo. Now, if the forward is exo, the backward is endo. Increasing the temperature will cause the reaction to go backwards, and that means I will have less yield of product. Do we understand that? What about when I add the catalyst? What is the effect on the rate of adding a catalyst? If it's a catalyst, that means it increases the rate of the reaction. Now, if I add a catalyst, what is the effect on the yield of products? Will it give me more product or less product? Remember that we said a catalyst will speed up both forward and backward reactions, so it does not cause the equilibrium to shift more to the right or more to the left. So actually you will have no effect on the yield of products, so the yield of products will be unchanged. Okay? Now, this is the same equation, and he says a manufacturer considers using a pressure of 5 atm instead of 10 atm. So he wants to use lower pressure. Predict and explain the effect on the rate of the reaction of changing the pressure to something that is lower. If I lower the pressure, what happens to the rate? Remember that we said if we're talking about the rate, increasing pressure increases the rate. Lowering the pressure lowers the rate. So the rate decreases for any reaction. Why? Because particles, when you lower the pressure, the particles are further away from each other, so less collisions. Remember, word pressure means you're pressing on the gas. So if you're using lower pressure, that means you have a bigger volume of the gas. You're allowing the gas to expand. So the particles are further away from each other, so they are less likely to collide with each other. Now, predict and explain. So here we were talking about the rate. Now he's saying predict and explain the effect on the position of equilibrium of changing the pressure to 5. Now, if I use a lower pressure, what happens to the reversible reaction? He said a lower pressure will cause the reaction to go to the side with more molecules. Remember that? So if I look at that equation, going forward will give me 4 of NO and 6 of water, that's 10 molecules. If I go backward, it makes 4 of ammonia and 5 of oxygen, so that's 9 molecules. So in decreasing the pressure will cause it to move to the right or to the forward reaction. So the effect on the position is the equilibrium shifts to the right. Why? In order to give more molecules, because we are using lower pressure, and lowering the pressure in equilibrium causes it to go to the side with more molecules, or increasing pressure causes it to go to the side with less molecules. You remember that? Okay, the other question says the diagram shows the apparatus used to investigate the rate of reaction between calcium carbonate and excess acid. So here he has it on a balance and he's drawing the graph of mass of contents. The mass of the flask and the contents is measured at regular time intervals, and the graph shows the results. We said, what is the purpose of the cotton wool that you put in the neck of the flask? The purpose of the cotton wool there, remember that this is a reaction that is giving out a gas. So we said when we have this, this is to avoid loss of solution from the flask by splashing. Explain why the mass of the flask and contents decreases. Of course, if you have carbonate with acid, why does it decrease? Because carbonate with acid will give carbon dioxide gas, and this carbon dioxide gas escapes. Okay, so you have to mention that it gives a certain gas and that gas escapes, because if nothing escapes from the reaction mixture will remain constant mass. The mass of a reaction mixture does not change unless if something is going out of the reaction. So the fact that the calcium carbonate and hydrochloric acid are reacting, if they form things that remain in solution, then the mass should not change. But the fact that there's a gas and the gas is given off, then the mass decreases. The experiment is repeated using same mass of calcium carbonate, same volume of hydrochloric acid but higher concentration. So the experiment is now using a higher concentration of acid. That means that the rate will be faster, and that means that the graph will look like this. Go down very quickly, but end up with the same final volume because we are using the same mass of the reactant. Explain using the particle collision theory how the rate of reaction changes with increase in concentration. Remember that we said if I increase concentration, what happens? I have more particles, so more frequent collisions, so faster reaction. Please add to that faster reaction, because he's saying explain how the rate changes. So you have to say first that the rate increases, add rate increases since more particles, so more frequent collisions. A student investigates the rate of decomposition of hydrogen peroxide solution. The diagram shows the apparatus he uses in this experiment. The equation for the decomposition is this. The student keeps the amount in moles of H2O2 in the solution constant at the start of each experiment. Now, state two properties of the solution that he should keep the same to ensure that the amount of H2O2 is the same. So when I say I want the same amount in moles, that means I need to have the same what? I need to have the same volume and the same concentration in order to have the same number of moles. Okay, the student carries out the experiment 5 times. He uses a different solid in each experiment to see how effective each solid is as a catalyst. So she's doing the same experiment but with different substances as catalyst. He removes the bong, adds a small amount of one of the solids and quickly replaces the bong. He records the time taken to collect 100 centimeter cubed of oxygen. Which solid does not seem to act as a catalyst? The one that did not give out any gas at all. So if it takes a very long time to give me a certain amount of gas, that is not really working. So the one that did not give gas at all is someone that's not working as a catalyst. Which solid is the most effective catalyst? Of course, the one that gives more gas in less time, that's the better catalyst. So to give 100 centimeter cubed in less time, that would be the better catalyst. So that is catalyst D. In the first experiment, the student added 1 gram of solid A. Describe what he could do with the contents of the conical flask at the end of the experiment to show that A was a catalyst, not a reactant. Again, remember, what was the definition of catalyst? Catalyst is a substance that speeds up the reaction without being changed. And that means if I add 1 gram of the catalyst at the beginning of the reaction, at the end of the reaction, I should also have 1 gram. So if I want to prove that A was a catalyst, I measure the mass of the solid A at the beginning of the experiment, that's 1 gram. Now, after I finish the experiment, this is a solid in a solution, so I need to filter first through filter paper and funnel, dry the residue between filter papers, and weigh. It should still be 1 gram. It shouldn't change. The student repeats the experiment using the same apparatus, but this time he records the volume of oxygen collected at intervals of 20 seconds. So he's measuring the volume every 20 seconds for new solids F and G. So he says the grade shows the results plotted for F. So he already plotted the graph for F, and on the grade he tells you plot the results for solid G. Now, when you plot these results, so this should be the points that you plot, and you join them, and that is my solid G. Okay? Use your graph to estimate the volume of oxygen collected after 70 seconds for solid G. So I look at my graph again. For solid G, after 70 seconds, I go up from 70 seconds to my solid G, go in, that is 82 centimeter cubed. Sorry, that's 82 centimeter. How do the curves on the graph show that the reaction is faster with solid F? Remember that if you have two graphs like this, solid F and solid G, which one is faster? It is F. Why is F faster? Because it has a steeper curve or it levels off earlier, that means it takes less time for the reaction to finish. The graph shows the volumes of carbon dioxide given off when marble chips are reacted with hydrochloric acid in 5 different experiments. So he gives you this curve and he says curve A, can you see where curve A is? It shows the volume of carbon dioxide given off when some marble chips are reacted with excess acid. So remember that the acid is excess, so we don't take it into consideration. Now explain which curve could represent the results obtained if half the mass of chips is used. Now remember that if I'm using half the amount of reactant, I should end up with half the amount of gas. So which graph gives me half the amount of gas that was in A? So that is graph E. Were you able to think of that? Because E produces half the amount of gas. Now, if I have the same curves and he's saying explain which curves could represent the results obtained if the reaction is done what? At lower temperature. So I have graph A. Now, if I repeat graph A at lower temperature, you should realize that at lower temperature means the reaction is slower. Which graph shows me something slower than A, but the same final volume because he's using the same mass of marble chips. That is graph C. The curve is less steep, but the same final volume of gas. Remember that he says explain which curve. So you tell him which curve and the explanation for it. Okay, the other question on the same curve says explain which curve could represent the results obtained if the marble chips were replaced by the same mass of powdered. So he's using the same mass, but instead of marble chips, he's using powdered. So you think powdered is faster or slower? Powdered is faster. With same initial mass means I need the graph that is faster with the same final volume of gas. So that is curve B. It has a steeper curve, so that's the faster reaction, and it will give the same final volume. Suggest a suitable piece of apparatus for collecting the carbon dioxide in this experiment. Of course, in order to measure volume of a gas from the experiment, the best thing to use is a gas cylinder. Okay. The other question says zinc is added to dilute hydrochloric acid. The equation for the reaction is this. An experiment is carried out using 0.12 grams of powdered zinc, excess acid, temperature 20. The volume of hydrogen collected in the experiment is measured at regular time intervals, and curve B shows the results that I get for these conditions. Now the experiment is repeated using same amount of powdered zinc, same concentration of acid, but at a higher temperature. So if I'm doing same amounts but higher temperature, which curve should show the results? Of course, curve A, because that is the one that is steeper and that indicates the faster reaction. Okay. Now the experiment is repeated again using what? Using 0.06 grams. So this is half the amount of the zinc that he used before, and everything else is the same. So if I'm using half the amount of reactant, I should end up with half the final volume of acid. So the curve that gives me this is this curve B was using 0.12. Now he's saying I want 0.06. So the curve that gives me half of it should be curve C. This gives half the final volume of gas. And that's the end of the questions on rates. Please study the chapter and again send me an email and I'll send you the quiz for the chapter.